Hello, everybody. Now we're gonna do the next homework assignment. It's 13.2. Make sure I'm on the right page here. Yeah. 13.2 homework assignment is calculus 3. The first question is asking, evaluate the integral from 0 to 1 of 2t to the fourth I7j. All right, let's look at that one. This is 13.2, number 1. Evaluate the integral, the definite integral, 2t to the fourth I 7j t plus 3k dt. When we integrate vectors, we do them by parts. So we have to do the first one, 2t to the fourth I dt I, 0 to 1, 7 dtj, 0 to 1, t plus 3 dtk. Right, so that's a constant that goes in front. The integrals, add 1 to the exponent and divide by that number. So we have 5t to the fifth, 0 to 1. That's I. 7 is a constant, so the integral of dt is t. So it's 7t from 7 to 1 j. The integral of t is t squared over 2 plus 3t from 0 to 1 k. Top minus the bottom. So we have 2 over 5, 1 to the fifth minus 0 to the fifth, I. Yeah. 7, t goes from 1 to 0, j. We do these separately. So we have 1/2 1 squared minus 0, 1 minus 0. This is k. So 1 minus 0 is 1, so it's 2 over 5 I. So that becomes 1, so it's 7j. So this is 1/2. And so 1/2 plus 3 is 7 over 2. K. Those are your component values. There it is. So it's 2 over 5, 7, and 7 over 2. That's the first one. Same thing for the second one. Question number 2 is giving us the integral from 0 to pi over 2 of 6 cosine t of I minus sine t of j plus sine squared of t k dt. Integrating each of these from 0 to pi over 2 individually. J dt, of course. Oh, the integral of 6 cosine, that's the constant. So integral of cosine is sine t from 0 to pi over 2 I. Integral of sine is negative cosine, so that becomes positive cosine from 0 to pi over 2j. Now the integral of, this is where it gets complicated. Easiest way to integrate sine squared t is if we use the identities, we know that cosine 2x is equal to cosine squared x minus sine squared x. Let me make this on the other page. So the integral of sine squared t k. So we know that cosine 2x equals cosine squared x minus sine squared x. That's an identity, which is why I gave you those sheets. Cosine squared is 1 minus sine squared x. This is also an identity. So we have cosine 2x equals 1 minus 2 sine squared x. Subtract, let's solve for sine squared x, because then we integrate the other side. So we subtract 1, so we have cosine 2x minus 1 equals negative 2 sine squared x. Change the signs. So we have negative cosine 2x minus 1. We'll change that so it becomes plus 1 equals 2 sine squared x divided by 2. So we know that sine squared x is the same thing as 1 minus cosine 2x over 2. So if we're going to integrate sine squared x dx, then it's easier for us to integrate 1 minus cosine 2x over 2 dx. Because with this one, we can split them up. So the integral of, that's a constant, so the integral of dx is x. Zero to pi over 2. Let's take the 1/2 out in front. So we're going to integrate cosine 2x dx. We already have that one integrated. So the integral of cosine 2x is integral of cosine is sine. But we also have to worry about that too. Since we had a 2 in front, we have to put the 1/2 out in front. Because if you took a derivative of sine 2x, you'd have cosine 2x times 2, and the 2 has to cancel since there's no 2 coefficient. So what we're looking at here then is one over 4 sine 2x 0 power of 2, which now makes it a lot easier because pi over 2 minus 0 sine 2 pi over 2 minus sine 2 of 0. So 1/2 times pi over 2 is pi over 4. Sine of pi is 0. Yeah, so that's 0. So it's just pi over 4. So all that just to get that as our integral for that part of our equation. Again, that belongs to this one. So what that one's going to be is all that. So I'll just put pi over 4. That one's already done. Plus our constant. No, we have this for definite intervals. This is k. So we have 6 sine pi over 2 minus sine of 0, I, cosine pi over 2 minus cosine of 0, j, plus pi over 4, k. Sine of 0 is 0. Sine of pi over 2 is 1. So it's just 6i. Cosine of pi over 2 is 0. Minus cosine of 0 is 1. So it's minus 1j plus pi over 4k. So those are our solutions. So we have 6, -1, pi over 4. Let's check number 3. State or solve the initial value problem for r as a vector function of t. The differential equation dr dt. So number 3. Number 3 gives us this information. Diff eq of dr dt 3ti minus 7tj minus tk. To find r, this is a derivative of r, so it's the v. So to find r, we integrate this function. So we have to integrate each part. T dtk. So the integral here, integral of t is t squared. So we have to have a t on the bottom. I, integral of t again is t squared over 2j. And the last one is the integral of t is t squared over 2k. Since it's indefinite, we have a plus c. So that's our r. We're given also our initial condition. At 0, we have 8i plus 6j plus 3k. So this is R0 at I, R0 at j, and R0 at k. Since that's just find our vector value function at t, our vector value function at t equals, because we have 3t squared over 2i minus 7t squared over 2j minus t squared over our constant is at the original function. So we have 8i plus 6j plus 8k. Combine the i's, we got negative 3t over 2 plus 8i plus negative 7t squared over 2 plus 6j plus negative t squared over 2 plus 3k. So these are our solutions. That's looking for the coefficients of that function. So this is going to be negative 3t squared over 2 plus 8, negative 7t squared over 2 plus 6, negative t squared over 2 plus 3. Sheet, that's sheet number 4. Solve the initial value problem for r as a vector value function of t. So we're looking for r of t. We're given d squared r dt squared as negative 18k with the initial condition r of 0 equals 40k. And we're given that dr dt at the original function is 9i plus 9j. Let's just put the components. So we know that this function here is our velocity. And this is our acceleration. So if we integrate our acceleration function and then combine it with this, which is our initial condition, then we get the integral of 18k is equal to negative 18t of k plus c. Well, the plus c are those guys. So it's 9i plus 9j minus 18k. So that's our velocity function. Now, if we integrate to get the r, we have to integrate the velocity. So we have to integrate each of these. So the integration of 9i is 9t. So there's 9tj. The integral of t is t squared over 2 plus our c. 9ti 9tj minus 9t squared k. Our the constant value is R0, which is 40k. So our final answers, 9ti, that goes in the first one. 9tj, this goes in the second. We'll combine these two. So we'll even do 40 minus 90k. Or we can do 90t squared minus or plus 40. So those are our solutions. 90, 90, and that one. 90, 90. You can either put negative 90 squared plus 40, or you can put 40 minus 90 squared. Okay, that's that much. Let's look at number 6. Crikey. Number 6 is a 2-pager. This one says, verify the results for the maximum height, flight time, and range of the ideal projection, or projectile motion. All right. So we have to prove that y max is that, the flight time is t, and that's r. Well, we know from our function, we have the horizontal and the vertical components. The horizontal, you have the initial velocity and cosine of theta at I. And then we have the initial velocity, the sine component of j. Now, what we did, part 2 of question number 6, so it's a long one. We know that the only force acting upon is gravity. So if we integrate the velocity to get it's a function of time, what we get here is negative g t squared over 2. So that is our k component, or the j component, but it's a vertical, it's acting down. So we have to take that into consideration when we're doing our equation. So that's 1/2 gt squared j also. So the vertical component, so the x component is x cosine theta. That's good. That's good. That one's wrong. That one's wrong. So it's got to be one of these two. If the x component does not have gravity, so the answer is C, because the y component is the initial value times the sine of the angle minus the gravity. The x component is the horizontal position, and the y component is the vertical position. Choose the correct solution. The reasoning: the projectile reaches highest point when its vertical velocity component is equal to the horizontal. No. Projectile reaches highest point where the vertical velocity component is unidentified. No. When the horizontal, no. It reaches highest points when the vertical velocity is 0. True. To find the vertical velocity component, we find the derivative of the vertical, of the vertical position. Choose the correct answer for this. Okay, so these are all functions of t. So the vertical position, as we said over here earlier, was v sub 0 sine alpha of t minus 1/2. So we're supposed to find dy dt. So there's t, so derivative of t is 1. The derivative of this function, the 2 comes down, so those cancel. So we have minus gt. So that equals a. V sub 0 minus gt. Set the vertical velocity component equal to 0 and solve for t. Choose the correct solution. T equals 0. Sine alpha, move the g of t over there, gt over there. And we're solving for t. So t equals initial velocity sine over g, which is a. Now that the time at which projectile reaches highest point has been determined, the maximum height is found by substituting the value of the vertical position in place of t. Yeah. Since we want to deal with the vertical positions. So we substitute what we just found, the vertical position, t into that equation, and simplify. So substitute v sine alpha, that's what t equals. Put it into this equation. So we get v sub 0 sine alpha, v sub 0 sine alpha over g. That's what t equals. V sub 0 sine alpha over g squared. That's the next one. We have v sub 0 sine, so that's v sub 0 sine alpha squared over g. We can distribute that. V sub 0 sine alpha squared over g squared. The g's cancel. So we have v sub 0 sine alpha over g minus v sub 0 sine alpha squared over 2g. Get a common denominator. So I subtract these 2 minus 1 is just 1 over 2g. Squared. So that's the first one, v sub 0 sine squared over g. So it's A. Thus, the maximum height for ideal projectile motion is Vmax, as we just figured out. To find the flight time for ideal projectile motion, choose the correct reasoning for the amount of time in the air. The projectile lands when its horizontal position component equals 0. Projectile lands when its vertical position component is unidentified. Projectile lands when its vertical position is equal 0. Projectile lands when the vertical position equals, no, that's not true. That's not true. Notice horizontal, the vertical position is identified. So the vertical position is equal 0. Set the vertical position component equal to 0 and solve for t. So we have v sub 0 sine alpha t minus 1/2 gt squared, set it equals 0, solve for t. What we see we have here is a quadratic equation. This tells us why we have a projectile that's in parabolic motion. So we can factor out a t out of both of them. And set equals 0. Yeah, it's up parentheses. Yeah, it is. So we took out t. So if we know that t is equal to 0 for one of them, and now we're going to solve the other one for t. So we have the initial velocity of sine alpha equals 1/2 gt, multiplied by 2 both sides, and divide by g. So time is equal to 2 initial velocity, the sine of theta, over g. Two initial velocity sine, which is equal to 0 is one of them, and b second. To find the range of the ideal projectile motion, choose the correct reasoning for finding its horizontal distance. The range of the projectile is determined by substituting the flight time for t in the horizontal position. That, yeah, because it's horizontal, is determined by solving. No, we just did that. By substituting the vertical. No, not the vertical. So the answer is A. Substitute 2 via initial velocity sine alpha over g in place of t for this equation and simplify. Cosine alpha times 2 sine alpha over g. And we simplify that, we got 2 VO squared cosine sine alpha over G. VO squared. This is an identity. So the answer is A. Thus the range is determined by that. And that does it. Oh, here they are. Those are the ones A, B, and C. So 1, 2, 3, 4 solve. Good luck, everybody.